the minimum cost of sorting. So when we are working with a comparison-based sorting algorithm, and you probably know merge sort is said to be optimal, asymptotically speaking, and it is. And so we know that n log n, oh, that's a terrible looking log. N log n is your lower bound for a sorting algorithm. So this is the best we can have. Now the thing is, why is this the best we can have? Well, for something where you have n distinct elements in a random sequence, and you are going to compare all of them. You have to compare them. So that's the thing. And if you remember merge sort, it has a really neat way of working. You start by dividing your problem, you conquer it by that division because you get to a point in which you have a single element and a single element is sorted. So they take advantage of that, and then you merge. So divide, conquer, and merge. And you probably know how to compute the asymptotical complexity of merge sort by now. If you don't, I'm going to do it in this video. But again, as always, as I have always been saying, I am assuming you to know programming to have a basic notion of asymptotical complexity and to have done a model about data structures. I was going to record videos about data structures, but I haven't yet, and it probably will take a while to do such series of videos. So, minimum cost of sorting, right? How is that achieved? And the Cambridge notes have a neat approach to it. It's really brief. They have, 2-3 pages about it. Maybe it's a bit too fast, I don't know. There's this great this great book, The Design and Analysis of Computer Algorithms by Alfred, John Hopcroft, and Jeffrey Holman. I'm going to put a link to the archive item. It's available in the library and you can borrow it. I don't know if it's because of the current state of the pandemic, or if it's going to be, or if it's something that has always been available, but it's there and you can read it. And there's this great video that I'm going to link as well from MIT OpenCourseWare, and they have and they start by the models of contagions, just like that book, and they do this proof based on the model of contagion that only allows comparison operations. And that's really neat as well. And the thing about theoretical computer science, and I'm mostly paraphrasing what the professor of that video says, but it's something I've always said as well, and something I think is really important and neat about theoretical computer science. You always have a model of computation. Actually, I said that I think I said that as something very similar in the beginning of this video series, and so I actually take some credit from that sentence, I guess, I don't know. Anyway, but the thing about theoretical computer science is that you always work in a model of computation. You define that model, and for this series of videos we have been adopting the RAM model and the random access machine model, and by defining the operations you have, the costs you have, you can prove that something is the best you can get or not. And then, well, you are doing reductions, and yeah, this model is analogous to that other model, and you do simplifications and all that. But the thing is, you know when you did something, and you can have some confidence about that, and that's something good. And you can extrapolate that from one thing to the other. So that's a good thing. That's something important, and it's a way of thinking. It's methodology. It's a tool, and that's good. A good thing to have and develop. So about this, what we want to talk about is how fast can we sort? What is the theoretical lower bound for a sorting algorithm that works on comparison, and as distinct elements in a random sequence. And so you have to make some points before doing any proof about it. The first point is exactly that. We are working with comparisons, so we count comparisons, right? And you can say, well, the count of comparisons is going to be x, for example. And the second point is there are n factorial comparisons. Sorry, permutations of n distinct elements. Permutations of n distinct elements. And please note, we are working. This is counting. You certainly already had a model about. We usually call these topics of elementary mathematics, so counting, things like this, or even probabilities. You have counting there, and so usually, and even in discrete mathematics, this is something more than covered by now. So n factorial, and now the thing is, you usually for merge sort you have a recurrence tree, and probably you have already seen something like this. T of n squared. If not, we are going to talk about it. T of n squared. And you know by the data structure model that the 8 of this tree, the number of elements of this tree is given by 2 to the 1, 2 to the 0 here, 2 to the 2 here, because we are going to have, you see, this is a full binary tree, right? So you have 2 to the 2 there, and so on and so forth. And on each decision you make, if you interpret this as a decision tree, so for example you have a yes here and you have a no here. If you go through this, edge. I think there is a better term for when you talk about trees. But if you go through this edge, if you think of it as a graph, and get to this node, you are cutting by half the number of options you have, right? So this part of the tree is no longer examined, right? So you divide it by 2. That's why you say that merge sort is logarithm, right? Of n, log n. And you see, for each element you do you have n, and then you do, yeah. Actually, yeah, I think I'm not, yeah. No, you have n elements, and you do that log n times, right? Yeah, log n times n elements. Yeah, obviously, yeah. So with that in mind, what you have is 2 to the you have 2 to the n permutations on the leaves, right? You do these comparisons, and you have the sequence, all the possible sequence on the leaves of the tree. And so you have, if you do to the maximum, you have something like 2 to the x, right? Because you are working with the number of comparisons. So x comparisons, right? X comparisons, and you have 2 to the x permutations, because that's the number of leaves here, right? This is going to be x, after a lot of development, and so you have x elements here, and you did you have 2 to the x elements here, the number of permutations, and you've done x comparisons. Okay, so with that in mind, if you want to know the number of comparisons x, you do x is equals to the logarithm base 2, I write LG for base 2, of 2 to the x, right? This is obvious, right? This was not a mathematical advancement by any means, but what is a mathematical advancement? Is something like, you can now say that 2 to the x is greater or equal, so it's greater, not strictly greater, than n factorial, right? So, with that in mind, you can say that x is greater than Lg of n factorial. By the way, this is not magic. You say that x is the absolute maximum of comparisons. So 2 to the x is the absolute maximum of permutations. And you have n factorial permutations. So the number of comparisons, x, is greater or equal to the logarithm of n factorial. That's how you get to the Lg of n factorial. That's how you get the number of comparisons, lower bound on this aspect, right? Okay. This is not all, right? Because, well, this is all. I'm going to show you how this is all. But I just received the call, so I'll be right back. I have to pause the recording and go solve an issue that I don't know yet what is. I'm back. Sorry about this interruption. They needed my help upstairs, so I went for help. I don't remember anymore where we were. Yeah, so we deduced that, right? So let's erase this mess and take more points, right? So we got this conclusion. Let me just delete this. Oh, oops. Okay. There we go. So, and my pen. The conclusion, right? So, each comparisons. Oh, let me. The right color. Each. Why can't I? Oh, got it. Each comparison. Each comparison is going to eliminate half. Eliminates half of the permutations, and we know that you have therefore x greater or equal than Lg of n factorial. So this is an important step. This is something important you have to understand. You have to realize. But that's not all, right? Because merge sort is optimal, and it is not Lg of n factorial, or is it? It's not. We're always told n times Lg and n, and that makes an intuitive sense as well when we looked at the asymptotical analysis on merge sort. We feel confident that it makes sense to be that. So what we do now is to show that Lg of n factorial is in fact approximately LGN. And how can we do that? So if you remember math classes, you know there's this guy Stirlings. I don't know if that's how his name is pronounced, but there's a lot of Stirling stuff that one studies, and we know the Stirling's approximation. The Stirling's approximation tells us that n factorial is roughly n to the n. And then by logarithm rules you say, hey, Lg of n to the n is the same as n Lg of n. And it's proved, right? If you don't remember the Stirling's approximation, then you have another solution. And another solution is to say, is to do a summation. Well, you have many solutions. You can do a Taylor series, you can do a summation, and a lot of things. But again, this is not a math class. We are just talking about algorithms and how you can't do these things. So for now and for the purpose of this video, you can just do this, and I'm happy about it. And if you want, you can do the rest. I've done the rest, it's fun as well. And if you like maths, you are going to love it. In the MIT video they do the summation thing, I think. In the Cambridge notes they also have the summation. It's often done and it's not hard at all. In fact, hang on. Give me a sec. Okay, so this is the, if you don't want to look at it, here it is. Let me just, there. And here it is. So this comes directly from Cambridge algorithm notes, and as you can see, there you go. As you can see, it's not hard. It's just you just send them, and then you do this conclusion. All terms to the right are less than or equal to Lg of n, and you can actually think about the logarithm function, and if you see. This is going to be Lg of n, so you go through that, and then you know it's bounded by an Lg of n. Yeah, and yeah, since it's monotonic, you do that. Yeah. But and it has to be. It's not complete. So yeah, because there's something else. Let me open it. Just a sec. Yeah. Okay. Now it's far more logical. Yeah. Because you have to show. Let me select this. Okay, this is the missing part, and now it's complete. Now it makes sense. Oops. Okay. Because I need that, and then you do all the way there. You are cutting off half of it, but this is asymptotically, so it's fine. Yeah. So you either do by Stirlings or you do this, and you have it. Anyway. that done, let's go on because we have a lot of things to do, and I want to show merge sort in this video yet. So this was just to show the lower bound on comparisons, pairwise comparisons. Sorry. So with that in mind, there's another thing, because when we talk about the minimum cost of sorting, you also have to think about the minimum cost of exchanges, right? And that's relatively trivial, because if you have n items in an array, then n exchanges will always be sufficient, will always suffice to put the items in order. In the worst case, n exchanges will actually be needed, right? So the worst case of the lower bound is intuitively n. That's something we feel confident about, right? But again, intuition isn't enough. You actually have to prove that. So you start by identifying the smallest, for example, in select sort. It's select sort. I think it's select sort. The one you have you go look for the smallest, you select it and put it. I think it's select sort. So I don't say wrong stuff here. Wikipedia. Exactly. You look for the smallest and you put it. So that's select sort. Yeah, select sort and the insertion sort. Yeah. So it's an n-square algorithm. You identify the smallest item present in the array, and if it's not already in the right place, then one exchange moves it to the right place, right? And a second exchange moves the next smallest item to the right place, and therefore, after n-1 exchanges, the items are all in order, because the last one you don't have to exchange that trivially, right? So it's n-1. So the bound is actually n-1 because at the very last stage, the biggest item, if you are doing ascending sorting, will be in the right place without needing a swap. But you can dismiss that concept. So I was reading Cambridge notes because they talk about this, and there's a second part in which they discuss a situation in which you have in the original arrangement of the data, you have the property that at certain position I is stored at position an item will need to end up at position I is always stored at I plus 1 with a natural wraparound at the end of the array. So every item is going to be in the wrong position, and so you must perform enough exchanges to touch each position in the array, and that certainly means at least n over 2 exchanges. Yeah, exactly. And they say it's good enough to establish theta n growth rate. Yeah. But then type-theta analysis would show that more than n over 2 exchanges are in fact needed in the worst case. Let me see if they have exercises here. They usually have good exercises for each of these topics. So maybe we have something like that here. Let me see. Okay, they do have an exercise here. The proof of assertion 1, which is the lower bound on exchanges, which I'm not going to write because it's trivial, convinces us that theta n exchanges are always sufficient. But why isn't that argument good enough to prove that they are also necessary? And that's a good exercise, let me think. Theta n exchanges are always sufficient, right? Yeah, so why isn't it good enough to prove that they are also necessary? Well, you can actually come up with a counterexample for that exercise. So yeah, and actually I'm going to add another exercise that I saw in the MIT notes. They make a proof that the source, the binary source algorithm is optimal. What we did here, it was for sorting. We show in this video that merge sort is optimal. But why is binary search optimal? It's even easier than what we have done here, and this wasn't hard. So I leave that as an exercise to the watcher as well. And if you want the solution, you have it in the link in the video that I will put in the description. In that same video, they also cover, I think, let me just have a quick look at it. Exactly, radix sort. So that's something I'm not going to cover in this series of videos, at least in the first part of it. I'm dividing this in parts. I'm not going to cover it in the... Why am I erasing all of this? I don't have to. Yeah, I'm just going to save this page and go to another one. So that's a good exercise, and you have the solution. And I'm not going to cover radix sort for now. So let's go for merge sort. And I'm jumping a lot of stuff here because it's like I said, I have a very specific goal with these videos, and so there are things I'm going to cover, there are things I'm not going to cover, and in the first stage, but it's like I said, the idea is to develop some intuition about some stuff, and I'm assuming a lot of pre-knowledge before this video, so yeah. Let's go then for merge sort, right? And I see that, yeah. So Cambridge has various exercises here, and they do a lot of stuff. Yeah, they have some good exercises here. I really recommend you to go through it. I'm not going to go through it now. No, nor am I going to do the merge sort as they do. I'm going to do some stuff here. And that stuff is the following. Let me just check something really fast. Because, let me just close the door because I'm hearing some noise, and that's not good. One sec, really fast. Okay. Okay. So I was seeing exactly what I wanted to do. I took some notes before this, you know. And so there are tons of ways of going through this, you know, really like a lot of ways. And the most pedagogical one isn't trivial of finding, you know. But merge sort is essentially an algorithm that has 3 parts. You know? Well, it actually has 2 parts. It's a recursive algorithm, but it has 3 key ideas, you know? The first one is sort the left, could be the right, the left half of the array. The second is sort the right half of the array. And I'm going to put a link to another video, a video about merge sort from Harvard. They teach this thing really well. Merge the 2. And actually, yeah, I should have done that for the insertion sort videos. I'll do the same. 2 halves together. So you see, assuming n greater than 1. So you see, you have these 3 steps. You sort the left half, you sort the right half, you merge them. And an important aspect to bear in mind is that a single element is already sorted. So, yeah. And then, again, I'm assuming you have functional programming and recursion, so eventually you probably already coded merge sort in a functional language. I did that in Haskell. In Cambridge they use OCaml, so something like that. They used it to use MEL, now they use OCaml. But anyway, it's all the same thing. Some places use Scheme, Lisp. There's tons of really great language, functional language. Just please don't do it with Python or something like that. Do it with a serious language. So, that. So let's write some actual code. And I will do the following. Correct me if I'm wrong. You need 2 routines, a merge sort routine and a merge routine. And merge, it's going to take a vector. I'm going to call V an element A and an element B. And if A is lesser than B, then M, it's the medium, is going to be seal is the top. Floor. It's floor, I guess. The floor of A plus B divided by 2, right? And I really did a terrible floor here, you know. Sorry. A plus B divided by 2. So this is oh, this is merge sort. I wrote merge. Sorry. That probably did a lot of confusion. Sorry. I meant merge sort. Merge sort. So, you see, this is the main routine, right? And as I said, you have three steps. So we are going to have 3 steps, but we need to know the medium, right? Because we are dividing and conquering. So dividing. So this is M, and let me write it like an M and not an N. So this is M, and then you do this if condition and you call merge sort of the vector A M, and you call merge sort of the vector from M plus 1 to B, right? And then you call merge of the vector with A, M, and B, right? That's simple, it's obvious. That's the easiest part of merge sort. But you need to write a merge routine as well. And so let's write one. And this is my suggestion. You do merge of vector A, M, B, right? Sorry. And you are going to need some variables, right? I'll write it single-lined. Otherwise we are going to run out of space. You need a E, that is going to be A, J is going to be M plus 1, you need K, that is going to be 0. So, while, and as I told you in the past video, it's always easier to do proofs based on while loops and not for loops, less confusion. So I'm going to use while loops. When I write the code, I probably write with for loop, but when it's to make a proof like this, I'm going to write with a while loop. Less confusion because it is more agnostical of the properties of the pseudocode you are using. So I prefer to work with that kind of structure. So you have I less or equal to n, and I'm going to use actually this, okay, and j less or equal than b. Okay, you probably already are understanding what I'm going to do here. If the vector at position I is lesser than, or lesser, strictly lesser than Vj, right? Makes sense? Hopefully it does. I mean, it's obvious, right? You start with hey, you have an index at j, you're comparing, because you see, you have two subarrays, right? You have this subarray and this subarray when you are merging, right? And that's why we are using 3 variables extra the vector. You do subarray from A to m plus 1, and the subarray, to m, A to m, and you have the subarray that goes from m plus 1 to b, and now you have to compare each of them to merge them in a single array in the right sequence. So that's what we are doing here. And if this condition meets, then you have an auxiliary k that takes v high, and high equals I plus 1. You increment high. You could do this in code, you could do this in one step. This is a post increment, but as always, if you are doing a formal proof, keep it simple. And even in code, it can be confusing to have that kind of thing here. And it's like, I never mistake, when I do a pre-increment or a post-increment, I'm always sure that that's what I mean. I am not going to do some confusion, but when I see someone else's code with that, I always wonder, does this guy know how this works? Because unfortunately a lot of programmers don't. They really should. When the programmer is careful enough to do this, like having a for loop like this, int high 0, high, let's already go lesser than 42 for example, plus high. If the programmer writes like this, he probably knows what he's doing with the increments, post and pre increments. If he doesn't, maybe he doesn't know how this works. So, and it's always easier to understand the code if you do things in a clear way. It's easier. It's easy when you know how things work. It's really easy to do hard to read code and having micro efficiencies. And just to take micro efficiencies out of it. For example, doing an anonymous function inside a function, just to, in some cases, it's more than justifiable. For example, to declare a comparator. Maybe it's easier not to create a whole comparator function, or if in Java a whole class just for that. Maybe it's easier to do a lambda function, and the code is going to be easier to read, but it's equally easy to save what? When if condition. You can reduce when if condition, you can often reduce a when if condition, a repeated if condition, with an anonymous function. That's going to mess up a lot the code. It's going to look way uglier. But you are going to save a comparison while adding an anonymous function. So maybe not an extreme saving, but you know, it's something a programmer knows, and therefore thinks, yeah, this looks great. I'm using an anonymous function here, maybe doing conditions with expressions. I think Rust allows you to do if conditions inside the return of a variable, the definition of a variable. So that's something I wouldn't do. The language allows that, but that's something I think would make the code way harder to read. So you have to do that thing. You have to think, do I want to do this, or do I want the code to be really simple and mistakeless? And maybe some constant coefficients in the syntactical analysis of your code that could have been removed. Maybe it's better to have them there and let the compiler do the optimization work for you. and maybe it won't be perfect optimization, but at least the code will be easily readable to everyone, and that helps avoiding bugs. Anyway, let's get back on topic, right? We are just writing a merge sort. So you have this if otherwise, and you know that if the person writes otherwise, maybe equals haskell. Args of k will receive v of j instead. You see, this if condition could be one line. Anyway, and you increment j instead of I. Okay? Easy, trivial. And despite this if, you are going to increment k. So you do that because you have to increment k because it's the index of the auxiliary array. After this while, you do another while. And this while is high less or equal to m. While high is less or equal to m, you are going to do, and let me just share something exactly. Aux of k gets v of I, and high receives high plus 1, and k, as always, k plus 1. And I think yeah. Sorry. Is this correct? The first while loop is obviously correct. The second, it's correct as well. Less or equal, exactly. Yeah. And finally, you need another loop to do the wait, isn't this in the wrong order? No, it's not. It's correct. And yeah. Okay, so the last step, and I'm going to write it here, it comes from here to there, okay, is for high from 0 to k minus 1, you do v of high plus a equals to house of high. Okay, it's a simple algorithm. There are some stuff here you need to pay attention, because this is an implementation that relies on some properties. Let me just save this page and open a new one. But you see, this is simple, but this is a very specific implementation. Okay, not that specific, but it relies on some neat stuff. And it was written to allow for very neat proof. So here's the thing: the last two cycles. Let me open it so that you don't have to remember them from memory. These last two cycles. they do not refer the positions from J to B, right? And that's and remember the J to B. Okay, this is A, B is B. They do not refer these positions because if they exist, they already are in the correct location of V, right? I'm just giving some time to let that sink. Because it's not extremely obvious, but it is, right? That's how it works. So you can dismiss this. You go from G to B in V, and you already have that. So you did in the otherwise branch of the if loop of the first. Of the if condition of the first loop. You already have J being attributed, and in the auxiliary array, and then you can, since you in the in the second loop you attribute V of I to the auxiliary when you are doing from I to M, so the others are already there. So the temporal complexity. Maybe I could show you an animation of this already. There are things like C-tutor website and stuff, and they should show this in animation. It's easier to follow from there. But I'll put the link to the Harvard video, and they already have an animation of it. And it's like this. It works like this. They do not show an implementation, but it's essentially this. This is a simple implementation. I mean, if V of I is smaller than V of J, then you use that in the auxiliary array. But when you do from I to M, you pick that value high from the vector and put in the auxiliary, and then you have this last routine that is going to put everything in V, and the other part is already sorted. So yeah. Anyway. Let's move on, right? So, hey, I'm back. I did a small pause because I went to have dinner, but I took that time to ask a friend if he found my pseudocode hard, and he said he did, and I know he knows how to write a merge sort. I hope. So I thought that maybe it was better to actually explain what I was saying to be trivial, claiming to be trivial. And there's no better way of doing that than using, as I said, there are animations and stuff like that. But Visual Algo is a website that has animations and lessons integrated, so I'm doing some advertisement here. It's funny that most videos I find at YouTube to have someone sponsoring them, and my videos is mostly me sponsoring others, so I find that neat. But anyway, this code is a merge subroutine in C++, and and you see, it's essentially the same thing I wrote, just instead of of being in pseudocode. It's in C++. So maybe some people find it easier to understand when it's in a language they are comfortable with coding and have some experience. Honestly, I'm comfortable with pseudocode, but sometimes it helps. So this is my last for loop. These are my 2 while loops. This is the merging part. I don't know if exactly. So and there you have the auxiliary array. So it's mostly the same thing I wrote. So yeah. You see, this doesn't have the merge sort, but it's just the merge function. It's a merge routine. But the other one, the other one is absolutely trivial. So if this can be confusing because it's recursive. Okay, this is not a good justification for it to be confusing, but it might take a bit to understand when you are thinking about an array and you are dividing and using various pseudo-arrays. It may be confusing in some aspects and in some manners, but they have here an example, so let's try that example, right? You see, you are dividing and then you merge. Oh, it's so yeah. You have here the steps. Exactly. And you see, let's actually repeat because I want to call your attention. Okay. So it's wait, pause. Why can't I? I'm sorry. Oh, I can't change when we are. I'm sorry about this. I wanted to put it to make it slower. All right, do your thing. Okay. So you see, I said that the last 2 cycles they did not refer the positions from J to B. So these positions are in this C++ code. J is m+1 in my pseudocode, so it's what they call right, and B is what they call hike. I think, yeah. And you see, exactly. So, oh, I thought it was the same, but actually it isn't. They are doing it the same way. Why are not they doing the same way? Oh wait. Ah yeah. Never mind. I misread it. Okay. I should be a bit. Oh, but they do here. Oh, they do the other way around. They do from the left to the mid. work with the array, exactly. And then they do from the right, which is the, what is the right? The right is my, okay, my k, exactly. No, my j, sorry, my j, and they go from there, the hike. Okay, can I make it slower? No, I can't. Let's see it at their speed. So they go. I see. I see. Okay, I honestly thought they weird, because if you, let me try to make an animation that uses my solution, because when I first wrote it I was quite confident it made sense. Now I'm doubting a little part of it. I did scratch a lot in the paper. I thought, yeah, I felt confident about it because therefore it must be right. Let me just write a simulation. I'm back. Sorry about all that away. So I actually looked for other implementations, and I was testing with other problems. But let me show you the solution I wrote. It's a bit different from the one in Gig for Gigs, which is the first result in Google, I think, and DuckDuckGo and so on. So, but I wrote this one. This website is C tutor, actually Python tutor, but it has a C tool as well. And this one here, I copied the comment with some changes from the Gig for Gigs solutions. But here it is. So the input is given by these two defines, the values of the array and the size of the array. And there's this merge function, which is essentially this. It's slightly different from the one in Visual Algo. It also is slightly different from the one in Gig for Gigs. The greatest difference is that I do not use this loop because the array I'm using is already duplicated in the here. You see? So this already allows me to jump that loop. So I have to pass v and the auxiliary array. This is exactly the code that is in Visual Algo. And yeah, so if we click Visualize Execution, we are going to have okay, we are going to have this. You can see the arrays here. So if you start iterating through it, you can watch the recursive calls happening, right? and it pointing to the arrays. And you can also see the variables. So that's really neat. And if we go to the part we were watching in Visual Algo, which is the merge routine here. So we can now go all the way to the last merge. And you see, I said that we would not need to copy the second half. And I think it's more obvious now that you see I'm using an auxiliary array that has the same values than the V. So if you start iterating here, you see that you can see the values changing here, okay? Oh, my cursor is not visible. Sorry about that. Maybe I can make it visible. 1 second. Okay, so it finished doing its thing here. Now we copy the remaining elements from V to auxiliary. And now we are on this step. So you see, it is going to copy 2, 5. Now 11. Wait. This isn't right. Wait. What? The hell? What? I thought I had written something that worked. Hate. Oh, because I was testing other inputs. I'm so sorry about that. Okay. The pseudocode can be wrong. Don't get them. I did not test the pseudocode in code until this moment. So, but I translated the pseudocode and tested it with some random examples from the internet. So, 1, 2, 5, 11, 15, 17, 19, 20. Okay, so n was wrong. Just that. Merge routine. I'm sorry. Yeah, and I was looking and I wasn't thinking. So let's go back here. So you see, okay, now it makes sense. Exactly. Oh. Now you see 1, 2, 5, 11, 15, 17, and 15, 17 is here, so we have to copy the remaining elements. You see, we sorted these elements, but now they are the remaining to the midpoint, yeah. So, in which exactly, so you go, because you are in K, and you are in this half. Yeah, and now the 20. And so, you don't need to go from J, and you can actually see J would be, well, J actually is 8, and K is 8, so, okay, wait, yeah, let me, oh, this goes all the way up, sorry. I wanted to see the variables, you know. For example, you have v of I, which is 2 lesser than v of j, and j is 7 at this point, so 17 versus 19. So it goes to the health. And K is 5. It's 5. And it becomes 17. Exactly. So when you do that, you go to the while loop next and you copy the remaining ones, which is hat K 6, so here, and V high, which is V2, which is here, 2 here, sorry, and then you go for the other one. The second half, J to B, it's already handled, so you don't have to worry about that. And you go to the copy back to the original array. And so you have 1, 2, 5, 11, 15, 17, 19, 20. And you see here you have in halves yet. So 2, 11, 15, 17. And here 1, 5, 19, 20. So these are the 2 remaining halves. And you have to do that. And you already did that here. So all you have to do is copy them up. So you don't have to worry about J to B. It's handled for you already. So yeah. This is only possible because we have an auxiliary array that has the exact same elements, right? Otherwise it wouldn't be like this at all. But you see, with this implementation, you only have I was asking myself another question. Yeah, sorry, I was thinking about another thing. But yeah, you only have this. So this is an efficient implementation, somewhat efficient implementation if you are working with two arrays, the one you want to sort and an auxiliary one with the exact same size. But yeah. Let me just pause the video because I'm thinking about something and I don't want to say something wrong before being sure I'm not being too stupid about what I'm thinking. Okay, so I'm back. What I was thinking wasn't stupid, it just isn't super relevant. I think it would be more confusing if I mentioned it than to just move on. Now, there are some things I want to say, namely, you can optimize this. This can be better than this took 230 steps. I actually wonder, but it's okay. It is counting. Yeah, it counts every line. Never mind. It's not a good method. But anyway. I think this is a nice implementation. I don't know. But my sort is that now that you know what I am talking about in this code, I think I can go back to the drawing area and let me then show the complexity proof. Also because I want to sleep. It's already late and I need to sleep. So that walkthrough and explain why I'm not doing a fourth loop. We have n elements, and an element is going to be B, which is the edge, the left, the end, the eiger, all these names, minus A, which is the beginning, lower, whatever you prefer to call it, plus 1. These are the number of elements to sort, the cardinal, etc. And if you look at merge, then it's quite trivial to say that merge is big O of n, right? And if you look at merge sort, well, then it's trivial to say that it is theta n, and I'm using big N. Well, I'm going to make this a small n, and LGN. And that's because you have t of 1 equals to a constant, C1, and you have and now this one is more relevant. You have T of n bounded by 2 times T of sealed n over 2 added with a constant, and it's a different constant than that constant, C2 times n. And that's true for any n greater or equal than 2. Right? This is based on the pseudocode, and we are talking about recursion. So, and like we talked about for the minimum cost of sorting, based on comparisons, you know that n is a power of 2 because we are talking about full binary trees. And the complexity of each level is going to be theta n, right? So you can say, based on that t of n is going to be in the order of complexity theta n log n, right? Because it's like we talked about. We have this tree in which you have t of n 2, and then you have t of n 4, and like you have this, right? And you are actually, let's see. So it's like you have this tree until you get to the t of 1, right here and here, t of 1 again, and all that. Till you get. So, and what I want to call your attention here is that you have, you see that C2, right? You have that here, C2 n. Here you have 2 C2 n 2, and you have 4 C2 n 4, right? And here you have C1 n. And these levels are like, I'm going to put it here in this color. This is all, right, how this is like 1 plus LG of n, the 8th of this tree. And so, in the worst case, you have omega n log n. In the worst case, the omega of the worst case is n log n. So you say merge sort is asymptotically optimal, right? And that's why it is theta n log n, right? It comes from that. So to write this in another way, let me save this page. Okay, so it's page 16. And let me open a new one here. So to formalize the idea, because this was all just intuition. To formalize the idea, here's the thing you have. you have T of n. T of n is equals to the system in which you have theta 1, and you have and now you have to define some functions, right? To abstract this away. So let's define d of n to be the time to split an array n in 2. Let mn be the time to merge two arrays of size an array of size n over 2, and let t of n, which we are defining there, be the total time of a merge sort of an array of size, and when I say size, I'm talking about length, n. Two arrays of size hence over 2 and of size n, right? Exactly. So this would be d of n, which is the time to split an array of size n. You split it, you do 2t of n over 2, the recursiveness, plus the n, which is the merge of n. And you do that in if n equals 1, if n greater than 1. Okay, that's fairly trivial. So if you do that, you now have to consider, you have to think, reason about d, m, and n, t, right? So what's the time to split an array of size n in 2? Well, you don't really need to do a copy of the array, right? You can simply do like I wrote in the pseudocode. So you have a function that takes 2 arguments, and in the beginning you go with 0 to n minus 1, and you have that m to find the mid position. So you just have to do an addition and a division. So it's constant time, right? So yeah, and the merge function. The merge function in constant time is not possible, right? You have 2 arrays and you have to compare the elements, so you cannot do that in constant time. But what about linear time? And you can, right? Because you go comparing, and in the end you have n comparisons and copies, right? You have n comparisons and copies. So that's theta n, right? It's linear time. So the time of a merge sort is precisely t of n is equals to theta n if n equals 1, and is equals to 2t n over 2 plus theta 1 if n greater than 1. So this is what you call a recurrence, right? And so you do that recurrence tree, and when you add up everything, you have the complexity, right? So this is the approach to find the complexity of this. But this is a linear reading. Linear reading. I'm not sure if this is a pronunciation, but this is a linear reading algorithm, and let me think what I was going to say. So I was saying this is a linear rhythm because linear and logarithm, but there are algorithms that have recursions and are, for example, logarithms, and have logarithm complexity. For example, a simple example. Yeah, for it is, yeah. For example, binary search, right? Yeah. So if you do okay, yeah. If you do, for example, yeah, so you have three common cases. You have the ones in which time is divided in a uniform manner in every level of recursion, and that's, for example, merge sort, something like this, right? Trying to give an illustration here. And you have examples in which I meant to design something else. Sorry. I'm already tired, so I'm thinking about something and I'm writing something else. You have things in which time is in a uniform manner divided by how levels of recursion. So things like this. This is like merge sort. So something like this. You have things in which you have, for example, the last level dominating, things like this. So it's more like, like that. And an example of this, I was thinking of searching, but searching would do it. Yeah, a binary search to find the maximum number of an array. Does it? I was thinking correctly, yeah. And you have cases in which you have the first level dominating the time, so things like this. And for this one, you have, for example, naive matrix multiplication, for example, in numerical programming, and that's something like this. Anyway, we are not going to get in much more depth regarding recursions in this series of videos for now, but for more you'd go with the master theorem, but that's not something we are going to cover for now. It's out of the scope here. By the way, usually t of 1 is equals to theta 1, so you don't really have to write this. Usually you only write this part here. Okay, just side note. And before stopping the recording, I'm just going to leave something here. As I said, this time I didn't follow the Cambridge notes, but there are some interesting questions here. Okay, yeah, there is at least one interesting question here. This one, let me just select it. So I'll leave this exercise as a closing of this video. It's a nice exercise. And then I'm going to sleep. So let me just my touchpad is somewhat broken, that's why it takes so long. Okay, so as closing of the video, and yeah, I'll leave you with this problem. Well, if it showed up, okay, it's there. So let me yeah. So yeah, that's the closing part of this video. Have fun, and till the next one. So till then, I'll sleep and solve other problems. See ya.